We've already learned to conceive systems, to think of systems as mechanisms of transforming signals. So for example, in this system here with one input and one output, the system acts upon the input u of t to produce the output y of t, and it does so according to certain transfer characteristics. So now what we're going to do is to define a tool to describe those transfer characteristics, a way of characterizing the process of acting upon the inputs to produce outputs, and its name is the transfer function. Well, there are two ways in which we can approach the concept of transfer function. In this video we're going to see the first one, and it has to do with differential equations. We know that one way to completely describe with no ambiguity the behavior of a system is to have a differential equation. So if we assume that the system is an LTI system, that is a linear time invariant system, its differential equation is like follows: the nth derivative of y plus a sub n minus 1 times the n minus 1 derivative of y plus all the rest of derivatives multiplied by their parameters plus a1 y prime plus a0 y, the output itself. And this is equal to the parameter bm times the mth derivative of the input plus bm minus 1 times u differentiated m minus 1 times plus all the rest until b1 u prime plus b0 u. This is the differential equation of the linear time invariant system. So now if we are given the input of the system, some u of t, we can solve the differential equation and get the output y of t. And we know that one way to do so is by applying the Laplace transform on the differential equation. So if we do that, for example, the term corresponding to the nth derivative gives us, or is transformed as capital Y of s times s to the nth power. This is n because here we are differentiating n times, minus the initial condition of the output times s to the n minus 1 minus the initial condition of the first derivative times s to the n minus 2, and we continue with all the rest of initial conditions. Well, this is a long term, but for example, in this one, in the first derivative, we would get a1 times, again, y of s times s, just one s because there's only one differentiation, minus the initial condition of the output. And we could do the same with all the rest of terms here in the input and also in the output. Now, if we are given u of t, obviously we can get u of s, and also if we are given the initial conditions, well, we have everything but y of s, so we can go to the expression and find y of s, and then inverse transform it, inverse Laplace transform to get the solution y of t. But if we only care about the transfer characteristics, those transfer characteristics we mentioned before, in a general sense, we can disregard the peculiarities that the initial conditions express. So we can assume all of them to be 0. So this is 0, and this is 0, this is 0, and the same happens in all the rest of terms. There are a lot of initial conditions which now are 0. In a way, this is like assuming that the system is at rest in the at the moment in which we apply the input u of t. Well, in that case, the algebraic equation we get in the S domain is a lot easier, and it is the following one: y of s, which is taken out as a common factor, is multiplied by s to the n plus a n minus 1, s to the n minus 1, plus all the rest of terms until a1s plus a0. And in the input side, we take out u of s as common factor, and this is multiplied by the polynomial bmsm plus all the rest of terms until b1s plus b0 plus b0. Now we can rearrange the equation to leave the y of s in the left hand side, and this is here bmsm plus b1s plus b0 in the numerator, and sn plus an minus 1 sn minus 1 plus all the way to a1s plus a0. All that multiplied by u of s. So here we have a rational function of s, and now you can realize that just by if we are given u of t, we only have to calculate its Laplace transform u of s and then multiply it by this rational function, and with that we have our problem solved, because we have y of s and as a consequence y of t. Well, this function which is multiplied by the input, or the Laplace transform of the input, is called the transfer function, and we usually denote it with g of s. So as you see, the transfer function can be defined as the transfer function is simply the Laplace transform of the output over the Laplace transform of the input when, this is very important, when all initial conditions are 0. And this is obvious from the previous reasoning, as you see, if you divide both sides by u of s, you divide both by u of s, and then this cancels with this, and you get here the transfer function according to this definition. Well, hopefully you now realize why we call it an external description, why this is an internal description, because we've somehow lost the detail that initial conditions gave us. Since we care only about the input output information, we've lost the one related to the particular state of the system when u of t is applied. And it is true that we lose information, but at the same time it's a powerful way to standardize the analysis of systems, because now we can compare different systems with different dynamics by looking at their transfer function, which has been obtained by assuming in all of them that initial conditions are 0. So before going to the next video, I'd like to make three final remarks. The first one has to do with the poles and the zeros of the transfer function. As you see, this is well, we have here a polynomial in the numerator and a polynomial in the denominator. Well, the roots of the numerator, the values of s that make this polynomial b0 plus b0 is equal to 0, the roots of this polynomial are called the zeros of the transfer function, or the zeros of the system. And the values of s in which the denominator is 0, n minus 1 s n minus 1 plus all the way to a1s plus a0. If we equal this to 0, by the way, this is called the characteristic equation. Well, the roots of such polynomial are called the poles of the transfer function, or the poles of the system. Well, both poles and zeros completely characterize the dynamic response of the system. And this is very important, because what we actually do in control, or at least in basic control, is to change poles and zeros of the systems in order to change their behavior according to our desires. The second remark has to do with causality. If you remember our video on differential equations, we mentioned that this exponent here, well, this order of differentiation here should be greater than or equal to, and should be greater than or equal to this order of differentiation here, and should be greater than or equal to m. And this is to preserve causality. The system to be causal, this must hold. So you can see that also in the transfer function. This exponent here must be greater than or equal to this. And if you come across a transfer function in which m is greater than n, you have to realize that there's some problem, that the transfer function is not describing a physical system, because it is not respecting the cause-effect relationships. Like, for example, that would happen if you think in a situation in which a table moves, and only after the table moves you start pushing it. As you see, it's completely ridiculous, but it is what the transfer function would be telling us if this is what we find in its exponents. Finally, I want to mention a further advantage of the transfer function, and that is that we can find the transfer function even if we don't have the differential equation. So imagine that we have a system and we know nothing about it. but we have access to its input and to its output, but we don't have any differential equation or any other kind of description. Well, what we can do is to perform experiments on the system. We can apply certain inputs like this step input or this ramp input, or maybe a sinusoidal one, or any other kind of input. We apply in one experiment or a series of them, and we register the outputs. We look at the output of the system and get the data of each experiment. I don't know. We have a bunch of experiments. So since we have signals in the input and in the output, we can always get or calculate the Laplace transform of the output, and obviously we have been able to calculate the Laplace transform of the input. And if we performed the experiments with the system at rest, with all initial conditions set to 0, then we have everything we need for our transfer function, because the transfer function g of s is just the Laplace transform of the output over the Laplace transform of the input. There it goes. And we've been able to find it just by using experiments. This process, well, the process is actually somewhat more complicated, but essentially that's what identification techniques try to do, to find the transfer function of the system by physical experiments. Okay, I think that's all. In the next video we'll approach the concept of transfer function from a different point of view.